Yeah. Okay, so take one of those and just pass those around. Actually, we'll see if Marshall can get around faster than you guys can get people. I'm going to stretch your brains a little bit. I'm sure you're all capable of it. Is the football team excited for playoffs? Yeah.
That's a very enthusiastic yes.
Okay, so we have figured out how to describe motion in one dimension. We spent a lot of time creating some equations. We know that my final position equals my initial position plus velocity times time. If I have constant velocity, we know that my final position equals initial position plus 1/2 times the sum of the initial and final velocities times time. If I have a final velocity and an initial velocity and the acceleration is constant, we know that I can find my final position if I have an initial velocity and the acceleration and time. And then we know that I can find my final velocity if I have an initial velocity and acceleration and time. And then our favorite, I know that I can find the final velocity if I have the initial velocity and acceleration and no time. And we've set up a strategy where we always know what formula to use. Even if we don't think we know what formula to use, we know what formula to use just by asking questions. Do I have time? If I don't have time or I don't need time, I have to use this equation. I don't have any choice. If I have a constant velocity, I have to use this equation. I don't have any choice. If I don't have a final velocity and I have acceleration, I have to use this equation. I don't have any choice. If I do have a final velocity and I need displacement, I have to use this equation. And if I don't need any distance information, I can use this simpler equation. So just by our simple series of questions in our strategy, we never don't know how to solve a problem, even if we think we don't. Okay, even if we think it's going to be difficult. Okay, so now we need to figure out how to do this in 2 dimensions. Okay, so that's our goal. And we remember our core, right? Our core is that energy gives rise to forces, which gives rise to motion. And we're doing the easiest thing that we can. We're starting with motion and describing that. And we've used position, displacement, velocity, and acceleration to describe that motion. And we've used motion diagrams, and we've talked about position, time, velocity, time, and acceleration time graphs. Now we're going to add a new kind of ominous sounding diagram. We're going to add something called a vector diagram. Okay? And don't let that scare you. Vectors are fairly straightforward. But we have to know something about trigonometry. How many of you remember SOHCAHTOA? Okay, SOHCAHTOA. No one else? So show me your hands. Do you remember SOHCAHTOA? This phrase right here, SOHCAHTOA. Okay, sine opposite hypotenuse, cosine adjacent hypotenuse, and tangent opposite adjacent. Okay, so some of you don't remember this, or some of you haven't heard of this before. In order for us to be able to do things in 2 dimensions, we have to understand this. Okay, so this first part is going to be a trigonometry review for some of you. For others of you, this is going to be brand new. So to introduce this, I want to show you why we need to use this and why this is going to be important to us. Okay, so consider the following situation. An airplane flies at a speed of 100 meters per second toward the east, and on an XY graph, that will be at a direction of 0 degrees, right? So the airplane's flying in a direction of 0 degrees, or straight east. At the same time, a strong wind is blowing north at 20 meters per second. And I'm sure all of you have occasionally thought about this kind of a situation where you've got something that's flying and wind is blowing it off its course. I'm not sure why you would think about that occasionally, but at some point in your life, you probably considered that situation to some degree. And maybe you even wondered, I wonder how we know how fast the plane is actually going. The plane thinks it's going 100 meters per second, okay? The plane thinks it's going 100 meters per second, but the wind is blowing 20 meters per second to the north. And this is how we're representing this on a diagram. Speed of the plane toward the east could be represented by an arrow toward the east with a length of 100 units, while the speed of the wind could be represented by an arrow toward the north with a length of 20 units. And it's very important to consider that this is 1/5 the length of this. Okay, so our arrows need to actually represent the actual values. Okay, I don't know if this is exactly 1/5 of that or not, or this is 5 times that or not, but let's assume that it is. Okay, so that's going to be very important to us because these ratios are going to tell us what we need to know. So hopefully it makes sense that because of the wind, some of the speed of the wind is going to be added to the speed of the airplane. Okay, so airplane thinks it's going 20 meters per second. The air particles they're around the plane think they're going 20 meters per second at an angle of 90 degrees to that. And a person on the ground observes the actual speed of the airplane. It observes the speed of the plane going 100 meters per second plus that 20 meters per second. So you would agree then, hopefully, that the actual speed of the airplane would be a little bit more than 100 meters per second because we've got some part of that 20 meters being added in there. Also, its direction isn't going to be directly east, but a direction that's a little bit north of east. Okay, the wind is going to push it off its course a little bit. But we need to know how much is the speed of the plane changed by the wind. Is all of the wind speed added to the plane speed? So do you think that the wind's actually going to be going 120 meters per second? Why would you think that it's not going to be that way?
So not in a different direction?
Okay, because it's not in the same direction as the airplane's going, right? Only if the wind was going in the exact same direction of the airplane would they add together arithmetically, or 100 plus 20. So we need to find out how much of that 20 meters per second is being added to the speed. So how much of the speed of the plane is changed by the wind? Is all of it added, or is only part of it added because the direction and the wind speed are different in direction? Because the plane and the wind speed are different in direction. We also want to know what direction the plane is actually traveling in. And hopefully you realize that before computers and calculators and things like this were around, this is how we navigated. Okay? When I filed a flight plan, I had to know something about the wind speed in all along the course of my path, or I'm not going to be able to get to where I'm going in an accurate way. Okay? So if I'm traveling by boat, if I'm navigating in a sailboat across the ocean, I need to know something about the wind speeds at various points in time, or I'm not going to be able to get where I'm going. So if we look at the above diagram, we'll find out that if we draw a line from the tip of each arrow, I'm going to draw a line from the tip of this arrow in the direction of the other arrow, and I'm going to draw a line from the tip of this arrow in the direction of the plane speed arrow. If I do that, I should get an intersection of those two lines at this point that forms a parallelogram. Okay, in this case it forms a rectangle, right? In other cases it won't form a rectangle, but it'll still form a parallelogram where the sides will be parallel. Then, and this is the important part, if we draw a line from the origin to the point where these two lines intersect, the length of this line will actually represent the actual speed of the plane. Actually represent the actual speed, a lot of actuals there, but will represent the actual speed of the plane. So this line represents 100 meters per second. This line represents 20 meters per second. And if I've drawn these lines to scale so that this is exactly 5 times the length of this line will represent the actual speed of the airplane. So if I can figure out how long that line is, I can figure out how fast the airplane is actually going. Okay, and you can see that the line is a little bit longer than the 100 meters per second, right? It's not going to be as long as the 100 plus the 20, but it is a little bit longer than the speed of the plane. So that should make sense. This line represents the actual speed of the airplane. Further, the angle between the axis, the x-axis, and the new line will represent the plane is actually going. Okay? So if I do this, if I create this parallelogram, the result, if I draw a line from my origin to the end of that where they intersect, will be the actual direction that the plane is traveling in. So if I can figure out what this angle is, I know what direction the plane is actually moving. So, is there some way that we can figure out how long this line is? And you all know this, right? You all know that you can figure out how long that line is, whether you recognize it or not. How am I going to figure out how long that line is? Yeah.
Pythagorean theorem.
Pythagorean theorem, right? This is a right triangle, and this is the hypotenuse. So if I know both of the sides, I should be able to figure out how long that line is. So, notice that the line we drew from the tip of the plane speed is the same length as the wind speed arrow. There's one other thing that we actually want to do, and although it makes sense to draw both of these vectors, and that's what we're going to call these arrows. These vectors are called, or these arrows are called vectors. If we draw these vectors from the origin, it makes sense to do that, but we want to be able to see the right triangle. So I'm going to transplant this wind speed arrow to the end of this plane speed vector. Okay, so we can do that. It's called it's part of what you can do with vectors. You can move a vector anywhere you want to, as long as it's still going in the same direction. So I could move this vector up here, I could move it over here. It wouldn't make any sense to do that, but I can move this vector over here to the end of this vector, and now I can visualize better that that's a right triangle. So if we move the actual wind speed arrow to this location, we can see that this is a right triangle. Is there some way that you know of? Of course there is. You should remember that we call the side of a right triangle that's opposite the right angle the hypotenuse. And you know that the Pythagorean Theorem tells us that for a right triangle, the square of the length of the hypotenuse, which is c, is equal to the sum of the squares of the other sides. So c squared equals a squared plus b squared. So the actual circumstance then is that the actual speed squared will equal the plane speed squared plus the wind speed squared. And if we substitute real values in for this, the actual speed squared is going to equal 100 squared plus 20 squared. And if we take the square root of both sides of the equation, we get that the actual speed is 102 meters per second. Okay? So with the wind blowing as stated, the plane is actually moving at 102 meters per second. Okay? And this all sort of makes sense, right? This is if we're observing this, we recognize that if I add some wind to the motion of the plane, I'm going to increase the speed. And we've now figured out by how much. And this is the easy part. You'll use similar Pythagorean theorem calculations dozens, if not hundreds of times throughout this physics course. So get used to doing that. But we don't want to just know the actual speed of the plane. We've got to figure out where we're going to end up if we want to continue this analysis. We need to know the direction the plane is now flying. And I want to find out what the angle is between the original direction and the new direction. Okay, so this is where our trigonometry comes in. Now, being able to do this requires a basic knowledge of trig, which some of you have not yet had in math classes. Even if you have, the review will be really helpful. Okay, so I just want to get a good feeling in how many of you have definitely not had this before? Okay, nobody's willing to admit that they definitely haven't had this before, so you've all seen it, and it's just not familiar, or there are some of you that haven't seen it. I don't know. Okay, so let's define some terminology. We've already stated the hypotenuse is the side that's opposite the side of the right triangle, okay? If I want to find the hypotenuse, there are two ways that I can do that. It's always going to be the longest side of the right triangle, okay? So that's always going to be the hypotenuse. Or if you identify where the right angle is, the 90-degree angle is, it's the side of the triangle that's opposite the right angle. So if I look across the triangle from the corner of that right angle, I'll see the hypotenuse. Now, I would highly recommend, because just like everything else in physics, it's going to work a lot better if you have a strategy. I would highly recommend that anytime you're presented with a right triangle, you know what sides are what. Okay, so I would immediately write down the hypotenuse and label that with an H. There's two other sides to the right triangle. We need a way to label or reference them. And how we'll reference them will depend on which angle we're talking about. Okay, because I have two other angles here, right? I've got this angle and I've got this angle. So how we talk about these sides of the triangle are going to depend on which angle we choose. So in physics, we usually use the small Greek letter theta to reference the angle. And for the triangle we're talking about, I'm going to label this theta 1 and this theta 2. It doesn't matter which one you label which. And oftentimes you're only going to label one because you're only concerned about one. You might not even label the other one, but it doesn't really matter just so long as you know which one is which. So the angle we're concerned about finding for the direction of the plane is theta 1. With reference to this angle, we can now label the other sides. The side of the triangle that is next to the angle, okay? Here's the angle, and here's the side that's next to the angle we call the adjacent side. This is going to be the adjacent side because it's adjacent. But you can say, well, Marshall, this is also adjacent to that angle. But we've already named it something else, so we can't call that the adjacent side too. We're just going to call this the adjacent side, and we're going to call that the hypotenuse. So we're going to label that A. And then we want to know what side is opposite the angle. So if I look across the triangle, I'll see the opposite side. And we're going to label that O. So we have an adjacent side, an opposite side, and a hypotenuse. Okay? Again, recognize it will depend on which angle you chose. If I chose angle theta 2 for my angle, then this side would be adjacent, and this side would be opposite. So make sure that you're aware which angle you're referring to. So on your diagram, let's also label our sides. This was the angle that we wanted, so this is going to be the hypotenuse, this is going to be the adjacent side, and this is going to be the opposite side. Okay? So, how does this help me? Okay. How does this help me? So for any right triangle, for a given angle, the ratios of the lengths of the sides of the triangle will always be the same. And this is the point of trigonometry that is not emphasized enough in our math classes. It's all about the ratios of the lengths of the sides. The ratios of the lengths of the sides will always be the same. And we're going to figure out what the meaning of sine, cosine, and tangent are related to that. Okay? So, as you become more and more experienced with physics involving right triangles, you'll become aware there are 5 features or pieces of information we want regarding the triangle. We already know that one of the angles is 90 degrees, but I also want to know the lengths of the other sides, or of all of the sides, and I want to know the other 2 angles. You'll find out, if you don't already know this, that if we have a right triangle and you're given information that gives me one of the non-right angles and the length of one of the sides, or if I have the lengths of 2 of the sides, I can get all 5 of the features, right? I can get all 5 of those values if I have one of the angles and one of the sides, or I can get all 5 values if I have 2 of the sides. And the ability to do this depends on the concept that for any right triangle, for a given angle, the ratios of lengths of the sides will always be the same. So let's use our airplane example to show this. So we've got our triangle. Notice that I've labeled the angle that we're interested in theta. Okay, so I'm calling that angle theta. And with reference to theta, this is my adjacent side, and this is my opposite side, and that's my hypotenuse. And if I look at the ratio of the opposite side to the adjacent side, my opposite side is 20, my adjacent side is 100. Okay, so that ratio is 0.2, right? 20 to 100 is 0.2. Stated another way, the length of the opposite side is 1/5 of the length of the adjacent side. And that's the key piece of information, that ratio. Now, what if we made this triangle 5 times bigger? Okay, here's my original triangle. I've kind of shrunk it down a little bit to make the comparison. So if I make this triangle 5 times bigger, the opposite side and the adjacent side, a ratio of 20 to 100 or 1 to 5 or 0.2, 2/10. If I do that over here, what do I notice about the ratio of the opposite to the adjacent side there? It's the same, right? It doesn't make any difference how big I make this triangle. The ratio of the length of this side to the length of this side is always going to be the same, no matter how I enlarge that picture. And this angle is also always going to be the same. Okay, so most importantly though, the ratio of the length of the opposite side to the adjacent side remains the same. It's 0.2. It's 20 over 100, 100 over 500, it's 0.2. Because all of the angles of the right triangle have remained the same, both the smaller and the larger triangles are stated to be similar. Okay, the ratio of this side to this side equals the ratio of this side to this side. And the angle here is equal to the angle here. So the other angles are also equal. They're not the same size, but they are similar. If they were the same size, what would I say they were? What's the term that we use for triangles that would be the same exactly? Starts with a C. Congruent. They would be congruent triangles. But these are just similar triangles. Okay? Now, this means that even though the lengths of the sides have increased, the ratios must be the same. So it doesn't matter how I change this. Okay? The ratio is going to be the same. So based on this reasoning, it should make sense for this particular angle of theta, the ratio of the length of the opposite side to the adjacent side will always be the same. So if the opposite side has a length of 2, the adjacent side has a length of 10. If the opposite side has a length of 7, the adjacent side has to have a length of 35. If the opposite side has a length of 15, the adjacent side has a length of 75. If the opposite side has a length of 2.5, the adjacent side has to have a length of 12.5. No matter what the length of the opposite side is, it will always be 1/5 the length of the adjacent side for that angle. It should now make further sense that if the ratio is some other value than 0.2, theta would also be different. Okay? If the ratio of this to this is not 0.2, then this angle cannot be the same. Now, if I had 5 and 12 as my ratio, the ratio is 0.416, 5/12 is 0.416. As this ratio is larger than in the previous case, this angle also has to be greater. It should then finally make sense that when the ratio of the length of the opposite side to the length of the adjacent side is a certain value, we can measure the angle that corresponds to that ratio. Right? If I have different lengths and different ratios here, I can measure the angle and I can write all of those values down in a book, and I can say if the ratio is this, the angle has to be that. If the ratio is this, the angle has to be that. If the ratio is this, the angle has to be that. we can write down all of the possible ratios of opposite to adjacent side, and we can put those in a book, but it really is annoying to say the ratio of the length of the opposite side to the length of the adjacent side. So we're going to call that the tangent. Okay? So the ratio of the length of the opposite side to the adjacent side is the tangent. And that's where the TOA comes in. Tangent, opposite over adjacent, right? SOHCAHTOA, opposite over adjacent. And if I increase this ratio, notice I increase that angle. If I increase this ratio, I increase that angle. Okay? At what angle do you think the opposite and the adjacent side would be exactly equal? At what angle do you think the opposite side and the adjacent side would be exactly equal?
90.
No. What angle is, so opposite and,
Oh, okay.
so it would be at 45 degrees, right?